Hi, this lesson is about solving exponential equations and logarithmic equations. So we start with exponential equations. So an exponential equation is one in which the exponent is the variable and the base will be some positive real number. So one way to solve exponential equations is by taking the logarithm of each side of the equation, and we want to use either common logs, which is just log, or the natural log, which is the ln function. Remember, common logs have a base of 10, and the natural log has a base of e. And the reason why we use either of those two is because not all answers are exact, and so some require a calculator. And remember, your calculator has the common log and natural log function already pre-programmed in it. Any other base would require a change of base formula. So try to avoid that by using either common or natural logs. So here's the first example of where we're going to use just that technique, where we will take the log of each side. So here we want to solve e to the negative x equal to 17.54. Now your goal is to solve for x, and right now that x is an exponent. So we need to get it out of that exponent position. And the way to do that is by taking the natural log of both sides. So here it makes more sense to use natural log instead of common log, because remember, the e to the x function and natural log functions are inverse functions. So that will allow us to simplify things more easily. So when you take the natural log of both sides, you can rewrite the left side using your log properties or log law by putting the exponent in front. So that's negative x ln of e equals natural log of 17.54. But remember that ln of e is equal to 1. So that leaves us with the next line, that negative x equals 2.86. You would need a calculator to evaluate that to get this. And then multiply both sides by negative 1, and you get that x is negative 2.86. So that's certainly a rounded answer. So, you would have to be told round to the hundreds. So otherwise, there could be a thousandths place, etc. So let's just make it clear that here we would want to round to the hundredths place, which is the second position to the right of the decimal. So here's another similar one. And here it really wouldn't matter whether we use natural log or common log, because the base is 5, and so either way it's not going to allow us to simplify easily the way we did in the last one. So I used common log just to show a different choice. So I have 5 to the x minus 1 equals 2. I need to solve for x, and x is in the exponent. So when I take the common log of both sides, that means that that exponent ends up in front as a coefficient of log of 5. So although it isn't exactly a coefficient, but the first log law allows us to put that exponent in front. So I have x minus 1 in parentheses times log of 5. Remember, log of 5 is just a number, equals the common log of 2. So here, this log of 5, which is just a number, is going to get distributed across. So I get the next line. I get x common log of 5 minus common log of 5 equals log of 2. And then add this to both sides, because remember, you're trying to isolate the x. And that gives us log of 2 plus log of 5. But then you have to divide by that number, log of 5. So we end up with this entire expression, the sum on top divided by log of 5. Log of 2 and log of 5, you can input them like that in a calculator if you want, but you could also use the log laws, collapse it down to a single logarithm. Remember, the sum of logs is the same as the log of the product, and 2 times 5 is 10. So log of 10 divided by log of 5, at this point you would have to input into a calculator exactly the way you see it. And here our x is 1.431. All right, so let's do another example. I have 15.6 to the x plus 2 equals 23 to the x. This time I have x's in the exponents, but in two different places, right? On the left and right side of the equal sign. I can again use either common log or natural log. I use common log again. So I took the log of both sides of the equation, which then allowed us to put these exponents in front of the logarithm. So that's what you see on this next line. I have x plus 2 log of 15.6 equals x log of 23. Distribute the log of 15.6 across those parentheses, so you get this line here. So that means I have to get my x's on the same side, so I subtracted this one over to the left, and I want to move this one over to the right, so that's why on this next line, you see what you see right here. X log of 15.6 minus x log of 23 equals negative 2 log of 15.6. All right, so from here, from this line to that line, I factored out an x because both terms on the left have a common factor of x. And remember, that's what we want to solve for, so we want one single x. And on the right side, I used a calculator to estimate that value. So negative 2 times the common log of 15.6 gives us the negative 2.38625 on the right. And then I actually used a calculator to subtract these two and then divided, and that value is negative 0.168603. And then just dividing these two numbers, I get 14.2 as a result. So here we round to the tenths. So remember what the tenths place is. It's the digit immediately to the right of the decimal place, which means that you look at the hundredths place to determine whether the digit stays the same or rounds up. All right, so that's one way to solve an exponential equation, which is to take either the natural log or the common log on both sides. So if you did the same problem using natural log, instead of seeing log, you would have ln, and in the end, you would get the same result. So you can try that on your own if you'd like. So here's another approach to solving an exponential equation is to rewrite both sides of the equal sign in terms of the same base. Now, this approach isn't always possible, but sometimes it is. And if it is, it makes things pretty easy for you. Because if you have the same base on both sides, then you can ignore the bases and just solve for the exponent. So if b to the x equals b to the y, then that means that x must equal y. Okay, now it won't always be so straightforward. Sometimes you have some work to do, like I'll show you in the next few examples. Here I have 2 to the x plus 1 equals 16. All right, so here my base is 2. And this is just 16 to the first power, so my base is 16. So according to this last technique I told you about, I need for them to both be the same. So I can definitely rewrite the 16 in terms of a base of 4, because 16 is 2 to the fourth power. And once I have this, two exponential expressions with the same base on both sides, that means you can ignore the base and just solve the exponent. So I have x plus 1 equals 4, which is what you see here. Then that's a pretty simple equation. Subtract 1 from both sides, and you get that x is equal to 3. And just like any other solution, you can always check it, make sure it works, by plugging it in. Is 2 to the 3 plus 1 equal to 16? Well, we know that 3 plus 1 is 2 to the fourth. 2 to the fourth is 16. The left side equals the right side, so you know that x equal to 3 is a good answer. Okay, example 5 is similar. Here I have a base of 5. Here I have a base of 25. I need to try to make those two bases the same in order to apply this technique here. Remember, it's not always possible, but in this case I will be able to, because 25 can get rewritten as 5 squared. But don't forget, you still have to square it, so that's why you see 5 squared squared. And 5 squared to the second power is just 5 to the fourth. So I have 5 to the x squared equals 5 to the fourth power. At this point, you can ignore the bases, and you're just solving x squared equal to 4. If you take the square root of both sides, I get two solutions, which is x is equal to plus or minus 2. So a positive or negative 2 would give you the correct answer. So two solutions. And you can check them the same way. You could check by plugging in 2, then check by plugging in negative 2, and you would find that the left side and the right side are equal. All right, so this one might not seem quite as obvious as maybe the last two. Here I have 3 to the 2x minus 1 equals 1. So on the left side, I have a base of 3. On the right side, I have a base of 1. So I have to figure out how can I make them the same. So I can rewrite the 1 as 3 to the 0 power. Because remember, anything to the 0 power equals 1. And once I do that, then my left and right side have the same base of 3. Then you can ignore the 3, and you're just solving the exponents. So then you're solving 2x minus 1 equals 0. Add 1 and divide by 2, you get that your solution is 1/2. Remember, the values of x for exponential equations can be any number, positive, negative, or 0, because the domain for exponential functions is all real numbers. All right, now we move on to logarithmic equations, and you're going to be using one or more of these techniques within the same problem. So with logarithmic equations, you might have a logarithm on just one side, you might have logarithms on both sides, but oftentimes you have to use your logarithmic properties or laws in order to compress or expand your logarithm. You're usually condensing them or compressing them when you're solving an equation. And then if you do have a logarithm on both sides, as long as they're same base, then just like with the exponential equations, if you have log base b of x equal to log base b of y, as long as you have a single logarithm on both sides with the same base, you can ignore the logarithm and just solve what you're taking the log of. So just solve x equal to y. Okay, and again, sometimes that requires some manipulation, and oftentimes that means you're using your log laws before you can get to that point. And the last technique is to rewrite the logarithmic equation as an exponential equation, and then sometimes you're using some of the techniques for exponential equations that we just talked about. Remember, by definition, if y equals log base b of x, then x must equal b to the y. And sometimes in order to get to that point where you can rewrite your log as an exponential, you first have to, again, use logarithmic properties to condense your logarithm. So there's a little bit more to keep track of with logarithmic equations. All right, so let's start with this example. Here I have 5 log base 32 of x equal to negative 3. Now I can't, I don't have logarithms on both sides, so this isn't going to help. But I can rewrite my logarithm as an exponential expression, but first I have to divide by 5. I need to have the logarithm all by itself on the left side. So that's what I did. I divided by 5. And so I get log base 32 of x equals negative 3/5. Then I'm going to use this skill right here, which is to rewrite my logarithm as an exponential expression. So that means that x is equal to 32 to the negative 3/5. Now we have to remember how to simplify exponential expressions. So the negative means that the 32 is going down to the denominator, so I have 1 over the expression that you see inside the radical. The denominator here means that it's the fifth root of 32 to the third power. The fifth root of 32 is 5. The fifth root of 32 is 2, because 2 to the fifth power equals 32. But then I have to cube that. So your final answer will be x equal to 1/8. All right, so let's try another one. I have 3 log base 10 of 2x minus 1 equals 1. All right, so you can actually solve this problem the same way I did this one, by dividing by 3 and then rewriting the logarithm as an exponential, but I'm going to show you a different approach. I'm going to use this skill right here where I have 2 logs on both sides with the same base. All right, so what I did first was I used my log laws to put this in the exponent of 2x minus 1. So log base 10 of 2x minus 1 to the third equals, and then I rewrote the 1 as log base 10 of 10. Remember, log, when you're taking the log of something with the same base, that's just equal to 1, and that's because 10 to the first power equals 10. So that's just a little reminder of how to rewrite logarithms in a different way. And once you have the same log on both sides here, base 10, you can ignore it, and I'm just solving this equation. So remember, you're solving for x. So what I did was I took the cube root of both sides. So I have 2x minus 1 equals cube root of 10. Then add 1, so you get 2x equals cube root of 10 plus 2. And then divide this whole thing by 2, and you get that x is about 1.58. So that's an approximate answer. All right, so here's another expression where, again, we're using the same skill because I have logarithms on both sides. But before I use that skill, I first have to move the 4, and the 4 becomes the exponent of 2x, which is what you see here. So I have the natural log of 2x to the fourth power equals the natural log of e squared. All right, so that means you can ignore the logarithms and you're just solving what you're taking the log of. So I have 2x to the fourth power equals e to the second. So if you take the fourth root of both sides, the fourth root of 2x to the fourth power is 2x, which is this, and the fourth root of e squared is e to the 2 over 4, which is e to the 1/2. Then divide by 2, and you get that x is equal to the square root of e over 2. Okay, so let's move on to the next one. Here I just have log base 10 of x equals -4. I'm again using the skill of just rewriting the logarithm as an exponential. Remember, the base of a common log is 10, so that means that x is equal to 10 to the -4, which is 1 over 10 to the fourth, which equals 1 over 10,000. Okay. So there's a little bit more going on in this one because I have multiple logarithms, but I have log base 2 on both sides. So most of the work up front is condensing this. So I have to use log law 1 and 3 because this becomes the exponent here, and this difference becomes a quotient. So that's what you see here. I have 2 log base 2 of 3 is equal to log base 2 of 3 squared, which is log base 2 of 9. Then the rest I just copied down. The difference of this logarithms becomes the logarithm of a quotient. So I have log base 2 of 9 over x equals log base 2 of 45. And so then you can ignore the log base 2's on both sides. you get 9 over x equals 45. And if you cross multiply, you'll get 9 is 45x, and then divide by 45. So x is 9 over 45, which means if you simplify, you get x is 1/5. Okay, this next one is similar in that you have to use your logarithmic laws in order to condense this side, because they're natural. You're using natural log on both sides, which is good, that all the bases are the same. So this becomes the natural log of x times x plus 2 equals the natural log of 3. Then you can ignore the logarithm, so you're just solving x times x plus 2 equals 3. When you distribute this, you get x squared plus 2x, which means you have a quadratic equation. So subtract 3 over to the other side. You're solving x squared plus 2x minus 3 equals 0. This is factorable. So that works out to be x plus 3 and x minus 1 equal to 0, which means you have two possible solutions. So you get -3 and +1. But you have to ignore -3 because -3 is not in the domain of your natural log. You can't take the natural log of a negative number. That's undefined. So the only one that works here is 1. And just like before, you can check it. You could have checked all of these. Is ln of 1 plus ln of 1 plus 2 equal to ln of 3. Well, ln of 1 is 0, and this is ln of 3. So the left side equals the right side. So 1 checks out. -3 is undefined. All right, so that's it for this lesson. Give the homework a try. Good luck.